Good evening, everybody. I find comets so fascinating, especially given how far they've traveled. And I say very far because some of the comets are amazingly distant. I'm going to start with a few pictures. Comet Halley rhymes with Sally. In 1910, there was a good apparition, and they took this picture. It must have been, they didn't have computers to control telescopes in those days, so they must have had some motor that would drive the sidereal time to follow the stars. And then they had to have an extra motor to push it a little bit so that the comet stayed in view. And they probably have, I don't know what emulsions were those days, maybe ISO 200 or something or other. And they had to have a long exposure. Can you see how far the comet has moved by the star trails? The brightest comet I ever saw was Hale-Bopp, and we saw two comets in a row. This one was visible in 1997, but it was discovered 2 years earlier because it was nice and big, and it was visible a long way out. I had recently started astronomy then, and I was too stupid to know that with comets, you never bother looking at the nucleus in high power. But when I looked at it under almost 200 power, there's a pinwheel pattern at Hale-Bopp, and that just blew me away. And I wish every time I observed, I'd made a little sketch and maybe do one at the beginning of a session and one at the end. And I think I could have seen how quickly it rotates, if that's caused by rotation. But it was really a magical thing to me. And I encourage you, if there's ever a bright comet, try that. If you look at it from the side, you wouldn't see that pattern, but it just happened that Hale-Bopp, the axis of whatever caused it, was in view. This is my favorite comet. Hyakutake came, it was discovered in the second half of January, and when you see 1996 B2, that mean was discovered in the second half of January in 1996, and that's how the system works. The letters go up as the months go on, as the half months go on. What I loved about it is the view was about half the sky. So if the comet nucleus is here, it went all the way halfway around the sky. It was just stunning. And I decided I would take one of my first astrophotos. So I had a telescope with no motor to it, just twiddly knobs. And I decided, well, I'll just try a picture. So I bought a roll of slide film, and I could only buy 36. You know, they had massive rolls in those days. And I looked through my telescope at the comet, and it moved compared to the stars behind it. And I was using the twiddly knobs thinking I'm tracking it, and I tried to be as careful as I could. And the comet patterns were jagged all over the place. It was a complete disaster of a photograph, but Dominic Derrick did a better job. I made this talk originally, and I told Paul I would give it because he asked for someone to fill in. And in 2012, another comet like Hale-Bopp was found a long way away, and I'll explain how they know how far away it is. And this was taken well before it got into close to the inner solar system. And Paul Martfield had to take 7 images of 2 minutes each. I don't know whether he used film or this or electronic. It was 2012. And with a big telescope, and this was really faint, and it got much brighter later on, but it ended up being a dud. The final comet broke up when it went around the sun, and it really wasn't that pattern that good. But apparently a whole bunch of comet experts were asked, what do you think about it? And a lot said, well, comets are unpredictable and we'll see. And one scientist said something like, oh, it's going to be awesome. It might be as bright as the full moon. So guess what the headline was? Anyway, it definitely wasn't, but I made this talk for that, and I've tweaked it a little bit for this talk. This comet, I saw it at sunset, and I remember looking at it, and just after the sunset, still in the bright glow, I could see the comet there. It was stunning. But what comets do is when they go around the sun in perihelion, they often are visible in one hemisphere before and the other hemisphere after. And the poor people in the southern hemisphere had to watch this. I mean, don't you feel sorry for them? Mind you, we were lucky of other things. So that, I didn't see it personally. And actually, I heard some of the best professional astrophotographers in Canada, Terence Dickinson and Alan Dyer, said, "Oh, do I ever wish I'd flown to the Southern Hemisphere for that," but they didn't, and it was just stunning. So what are comets made out of? If you ever talk to a school group, something neat is to build a comet. And JPL has a video of this. And you basically have water and dirt plus some starch, syrup, vinegar, alcohol, ammonia, whatever you want, and dry ice. And it's easy to pick up. You just put it in a cooler. I didn't trust the dry ice in my car. I don't have a trunk like it's one big unit. So what I did is I drove with the windows open. Unfortunately, no policeman stopped me because I was drunk or anything. But you've got to be careful if this is in a room. It's better to let it sit for a day, and that gets it a little bit more punky, because what you've got to do is pound it with a hammer and break it into pieces, and then you mix the water and everything together in a bag with insulated hands, gloves, and you get this. Just to show of hands, has anybody ever seen somebody make a comet in front of Freddie? It's really neat to do, and the kids are so engaged because you hold it out to them and they can feel it. Well, I don't want to touch it that cold, but anyway, it's a neat thing to do. And I suspect these people added some ice cream as well, but I'm not sure. But that's not that accurate a view of comets. I thought it was perfect. They are made of dirt, water, dry ice, all frozen together. But comets actually reflect very little light. They're almost as little as this poor bird that is about to be dawn treated to get rid of its oil. The other thing is most comets have an irregular shape like this one. The ones whose pictures I've seen are not round like anything. They're typically this sort of shape. And I don't know it would be possible to add enough black paint or something rather to the mix, or something else, and to shape it to be more like that. But it's pretty accurate as a view of what a comet is. I'm going to describe two missions, and I wondered about adding the Rosetta mission that actually landed on a comet. And I said, no, I'll leave these two because they're both neat, but later on they landed. Unfortunately, the lander, there's a saying, for want of a nail, a horse was lost. And for want of a working thruster to hold the lander onto the comet, it bounced and it ended up getting caught in a crevasse, and it lasted until the batteries wore out, but the solar panels didn't provide energy. And that's too bad because they had awesome experiments planned, but you know, c'est la vie. Anyway, deep impact. No quarterback, even the best, can aim as well as these guys did to hit the comet. So the comet's moving. It's not necessarily moving in the direction of the tail, because when it's leaving the sun, the tail is pointing in the direction it's moving rather than behind it. Anyway, the mothership fired this lander that took some pictures and sent it back, and the mothership took all sorts of pictures, and let's see if this works. Boom. Oh, it came again. So they did all sorts of measurements of what happened when it landed, and they came to the conclusion that it was soft as a snowbank, which was later refuted by the Philae lander that Rosetta had, and it had less water, more dust, and more organic chemicals than expected. But they actually did that experiment. One model of a comet is that you have a layer of tar carbonaceous material around the outside, and you have different jets that squirt chemical, like dust and dry carbon dioxide and water out. And so that's how a comet works, and eventually it gets smaller. And maybe that explains the pinwheels from Hale-Bopp, and also the striated pattern of that the poor people in the Southern Hemisphere had to watch. I'd love to have seen that, but c'est la vie. Second mission I'm going to talk about is Stardust. And what the Americans did is they sent this through a comet tail, and they collected the bits of dust in a very interesting way. And then this ended up landing in Utah, and they did their research and they came to this conclusion. So here we go. They made a chemical called aerogel, and it's almost only a little bit denser than air. So it's really fluffy. And they put this in the device, and they went through it, and the particles, instead of hitting something solid and then they'd crack open, they slowly slowed down, so they were able to get individual particles that haven't been damaged. And so they got them, and they did all sorts of tests, and they were surprised that some grains had CAIs. I didn't know that term either. Calcium aluminum inclusions are something found in meteorites, between other things. And when they do radioisotope tests, they're able to date it. And 12 years ago, the oldest thing in the solar system was this 4 billion and a bit years. And when I looked it up to research for this project again, it was the same year. So that research hasn't changed. I would have thought they might have updated it, but that's it. Now, a key thing that I'll get to later is that CAIs only form in a hot place. And that's a problem that, to my knowledge, hasn't been resolved, 1300 K. How do comets form? All right, so this is a picture of the star Beta Pictoris, and they're very carefully monitoring it. It's a relatively young star, and I'm just going to try and illustrate here with my hand. When you have a nebula forming that slowly turns into a star, there are molecules moving all over, but it turns out there's a net rotation in one direction or another. It could be like this or like that. Now, what happens with that rotation is you sometimes get particles going up if the plane is like this, and sometimes go down, and when they hit each other, they sometimes collide and they end up going mostly straight. And this is a mechanism for things to flatten. And in my opinion, most astronomical objects are either spherical or roughly spherical or flat, like Saturn's rings, galaxies, solar systems, etc. And that's the factor behind it. Anyway, they got collected this. This is from stardust, and you end up with small particles, and electrostatic attraction happens. Like, there's very little gravity between small things, but these attract together to form bigger things. And over time, when these things are drifting around, they get bigger. And eventually they reach a size where they have gravitational attraction. And as everything is slowly drifting around, what they do is they gravitationally attract and join each other. And you end up getting the basis for solar systems and stars and whatever. I tried to do more research on that, and I didn't get as much information as I wanted. Now, in any solar system, once the star ignites, it's going to be hot in the inner solar system, but colder further out. And it turns out when you're in the inner solar system, the rocks and metals condense like Earth, but the hydrogen compounds, including our favorite, water, stay vaporized. If somebody pours some water over the moon, it's just going to vaporize and go into space. Similarly, when a comet with water vapor in it goes into the inner solar system, it's going to sublimate into space, and we see comet debris. Now, when you're further out, it gets colder, and then the hydrogen compounds do collect. So the message there is that it's far away that it's cold enough for comets to form, but the CAIs, calcium, aluminum intrusions, need the heat. So how could you get those things that are close to the star all the way out to where the comets are? And to my knowledge, there's no answer yet. What makes the tail? Well, there are two tails, actually. Has anybody seen both tails of a comet? There's a blue one that is an ion tail, and it's pushed away by the solar wind, and it goes straight away from the star, or our sun, of course. But there's a dust tail that is pushed by radiation pressure. Every photon going through has a little bit of momentum, and when it hits a dust, it nudges it a little bit. Now, this doesn't perfectly follow the distance away from the sun, but it's the tail that we most can see from the dust. And as a comet approaches, the tail gets longer as it gets closer to the sun. And then it turns around and it goes back. And the key is when the comet goes away from the sun, the tail is ahead of it. And lots of people think the tail follows the sun, but not so. Ron Macnaughton gave a talk once. And I was watched him. I think it was Neath, but I'm not sure. And he just looks like a friendly guy, and he came across as a friendly guy, and he loved spending hours looking through his scope. Now, I think at Neath there were some mounts that were, not that much money, $30,000, $40,000 for a mount. Now, do you think he spent $30,000 or $40,000 on Home Depot to get his mount there? What do you think? Yeah. He put this together and he observed 7,000 hours looking for a comet before he found his first one. And that would be 3 years at 6 hours a night, every night. Wow. Talk about commitment. And it took him the same amount of time to get his second comet, but then it was less time to get his third, fourth, up to 12. He found 12. Unfortunately, he passed away a few years ago. When you find a comet, you look for a fuzzy patch that doesn't have stars like a globular cluster or isn't on the Messier list. And what you do is you look for it to move. And then they suggest you call a friend and say, I think I found a comet. Could you look at RA this and DEC this? And the friend will fire up his telescope or her telescope and look at it and say, yeah, I see it as well. And they encourage the reports. But they said that 4 out of 5 reports of a comet are duds. And they've got to check it. Now, I'm going to talk a little bit about how objects move around the sun. They follow what's called a conic section path, and you can make a conic section by cutting a cone in a certain angle. If it's not that steep, it's an ellipse. If it's parallel to the side of the cone, it's a parabola. And if it's closer to straight up and down, it's a hyperbola. And the different paths depend on different properties. I used to teach high school, and my grade 12 physics students were to draw a diagram of a real comet where everybody had to pick a different actual comet. And they had to draw an ellipse to show the shape and also draw the circle for the Earth's orbit. You use string and you just wrap around 2 pins, and that makes it work. Now, 1 pin is going to be where the sun is, say the yellow one. The other one is not really a big point in the solar system, but if you're in a room that is shaped like an ellipse, make sure you're not sending it one focus and you dish your boss, who is standing at the other ellipse or other focus, because the reflection will transmit the little talk a long way. Now, a key concept in any conic section is eccentricity. And the major axis is the long direction of an ellipse. And basically from the center of that axis, the pins are 54% of the way to the outside. So if the eccentricity were 0, both pins would be the same place and it would be a circle. And if it were bigger, anybody know where this is? Pardon me? Yeah, that's a DDO. They had a big conference there, and they made this to be the shape of a specific comet's orbit, and the eccentricity here is 0.85. So that means from the center of the ellipse to the sun is 85% of the distance to the comet orbit, which is the curve going around it. And that is comet 2P Encke, which obviously was the second periodic comet to be found. And its Q is the perihelion distance. And if you look at the distance between the sun, which is dot, and the end, it's about 1/3 of the distance to the Earth, the astronomical unit that I've shown. And I equals 12 degrees. Anybody want to guess what I stands for? In terms of an orbit? Sorry? Yep. The inclination, our planet is on a flat plane with which the sun is also in it. But a comet also is on a flat plane that is usually tilted compared, and it actually goes on that plane, and the I is the inclination or the distance between the two. Now, there are a couple of other angles that are part of the defining an orbit, but I'm not going to go into them. So here's Comet Wild 2. Its inclination is 3 degrees, so it's almost in the plane of the solar system, so it's easy for us to reach it and get back home again. So it's being used for a number of missions. 1.6 AU is about the distance to Mars orbit. My favorite comet, Yakutaki. And what was magical about it, I don't know if I can point. Yes, can you see the cursor? Can you see the cursor? On March 25th, remember it was only discovered in January. On March 25th, this comet, just a minute, what am I doing wrong here? This comet was fairly close to Earth, so it was moving quickly compared to the distant stars. And like I say, 90-degree tail, just stunning. When it went past perihelion, then the people in the southern hemisphere didn't get as good a view as we did, but they can't get everything, right? Sorry, I couldn't resist showing you another picture. So in summary, if the eccentricity is less than 1, it's going to be bound. If it's exactly 1, then it's a parabola, and it, in theory, starts from infinity, goes around the sun, and then goes back out. And there are a number of comets with that. And if the eccentricity is greater than 1, it escapes. So the path of an object around the sun is defined by 6 numbers or elements. I talked about perihelion distance and eccentricity. Eccentricity gives the shape. Is it round or is it long and narrow? Date and time of perihelion, inclination, and the 2 angles that I'm not going to explain. All right. Is there a separate mic I can hold? Oh, I can just take this off, right? All right. So if I can you hear me still? All right. I have 2 pictures here that I took when the New Horizons spacecraft went to Pluto. This one was followed 2 days later by this one. And there's a dot that is Pluto on this side in the upper one. And 2 days later, it's on this side. I don't want to spend a lot of time on this, but did anybody look at it and see the dot that has moved from one side to another? And if you just tell me where to move the pointer. Okay, are you telling? Okay, so you're in this one. So where do you want me to go? Left, left, left. Ah, that was Pluto the first day. Now, did you find it in the second picture? So where do I go? Well done. Well done. That's a fun thing to show kids, by the way. They get so excited, me, and they really enjoy it. And to actually see a planet move in the sky. And I felt like when I saw Yakutaki move compared to the stars. That was such a wonderful moment to me. Okay, it's still on. Then what they, unfortunately, I only did 2 measurements. I wish I'd done 3. Because if I had done 3 measurements, there's some formula, I don't know what it is, but they actually find the 6 elements of the orbit, and it would give a rough idea of where that object is going to end up moving. It's a little more complicated by this. But then what they do is they say, well, okay, this says the comet's going to be here in 2 months, but it also says it's going to be back here 2 months ago. And then they can find images for that, are taken, like there's this file of images of the DDO. I don't know if it's still there or not, of old images, and they find an old image. Oh, we didn't realize, but that's the actual thing we've seen. And when they get more data, they get a more accurate measurement. Now, I took, for my research for my talk in 2012, a dozen years ago, I downloaded a list of all the comets with all the orbit element data. And I processed it with Excel, and I made a graph. And at the bottom of the graph is the eccentricity. So at 0, it's round shape. And at 1, it's a parabola shape, and so on. And the second is inclination. And I've got names of a number of them. I just point out the periodic comets that are orbits of less than 200 years. They have a number with P and then the name of the person that discovered it. And it looks like Hartley had discovered more than one. The other objects, and I didn't have space to do it all, if it's one that just comes out of the blue and not periodic, they have a C/, and then they have the year, and remember, that's the second comet in the second half of the year, and the Yakutaki is this Japanese guy that found it. Now, it turns out that there's a whole group of comets down below that have periods of about less than 200 years, and they're called periodic comets, and they have a problem with them. Every time a comet comes close to the sun, it gives off a tail. And what's the tail made out of? Stuff the comet was made out of, right? So the comet gets less heavy, and the estimate is a comet can last a few hundred orbits. Now, a few hundred orbits of comet Halley is 15,000 years. Now, that's a long time for me. I'm not going to live even to the next apparition or appearance of Halley. But cosmically or geologically, that's just a drop in the bucket. So fairly soon, this comet will not be put on a show anymore. And so where do new comets come from? And a Dutch astronomer, Gerald Kuiper, said, maybe there's a series of comets stuck way out there, far away. And he figured, given that most of these comets are in the orbit of the solar system, that it would be relatively flat, and it was end up calling the Kuiper Belt. And this is something like 20 to 50 AU. But there are other comets where the eccentricity is almost 1, which means that's either a very long orbit path or infinitely long. And those comets come from what they think is the Oort cloud by another Dutch astronomer. They seem to like comets. And it's much further out, and it's completely spherical. There are comets from all directions, and comets like Yakutaki, with an eccentricity that's almost 1, they come from way out there, very far away. And so that's our pattern. How do the distant comets get in? Well, there might be other objects there, maybe a big planet, but even if there aren't, if it's a small object, and if a comet goes just in front of another object, it's going to attract the other object that gains energy, so the comet loses energy and goes inward. Now, if it turns out it goes behind another object, the comet gains energy and the planet or whatever it is loses. All right? So it doesn't gain. But what about a comet that comes close to, say, 20 objects and everyone just in front? So it comes across, it bends in, comes across again, it bends in, and it keeps getting deflected inward. Now, that's pretty unlikely, but it's we're talking about trillions of comets and a lot of events. So maybe that's how they come in, or maybe it's just one star, or maybe one planet it hits. So my last question is, do comets travel to us from beyond the solar system? Believe it or not, they've found comets around other stars. This Beta Pictoris, they've looked at it by telescopes and monitored the brightness. And it turns out when a comet comes, there's sometimes when the brightness of the star drops in a certain pattern that matches what they thought comets would, and it ends up being, they figure it's a comet, and they found 30 comets around this star, including a bunch where they happen in a row, blunk, 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 and they figured there may be a comet that was split apart, which comets do, and there were several tails in a row that went across the star, but there are comets out there. Now, if you look at the bottom right corner of the graph, there are a few of them that have an eccentricity of above 1, which means they're hyperbolic. And probably these 4 comets, again, this is a dozen years ago, the eccentricity is big enough that they're going to have enough energy, they're going to go, but maybe they're going to go near a planet or somebody that then they don't leave. And we don't know because we can't see comets when they're, 300 astronomical units away. Now, there have been since then some interstellar objects. The Ison comet is a little bigger, and whether it actually leaves the solar system, who knows? They include Voyager 1. I took this from Wikipedia, and it's 1.2. The Voyager is 3.72. Now, it's not a comet. It's being fired by a rocket. Oumuamua. You've all heard of Oumuamua, right? And Oumuamua is 1.2, and it definitely came from another solar system. And Borisov is 3.36, and it also is definitely an exocomet. Now, somebody made this graph with, there were different dates, but they put both on. And you see how Oumuamua comes from north. It went close to the sun, so it has a sharp bend, and it went out. And unfortunately, it was only detected when it was leaving. If we had detected that when it was coming in, imagine the data they could have got about that object. But it was madly leaving when we finally got. Borisov is this comet here. It was a much further away from the sun at perihelion, and it bent only a little bit, but it's definitely an exocomet. So, oops, I meant to say something. Astronomers have only found 2 objects that are definitely exocomets. So is it going to take a long time to find the next one? Maybe not. You probably heard about the Vera Rubin Observatory in Chile, and it's going to do a survey of the sky and get amazing information. And the head of communications held up a model. This is not the real chip. In my computer, the chip is about this big, or my camera, I mean, is about this big. Look at how big that chip is. It's the biggest one. And they think, oh, that's the full moon that they put on it. And they figure they can take the visible sky from that location every 3 days. And they're going to be able to then get computers to analyze, day 1 and day 4 and say, oh, something is moving, and they're going to make alerts. And the number of new discoveries that are going to come out of this is amazing. So there are lots of visitors from very far to be discovered, and I think they're going to come up with some really neat things. Anyway, thank you very much. I'd love to have some questions. Thank you. I think Tom wants to use the microphone. Yep.
Hi. Any further comments about Oumuamua? Can you hear me?
Yes.
Yes. Any further comments about that Oumuamua? Because Avi Loeb says that it's an artifact.
I'm sorry. Comments on Oumuamua? Yeah. Okay. They only could see it. Like, I'm very good at taking photographs of animals' tails as they're running away from me. So we were doing the same thing with this, that it was already going away. And when they had a run at a certain telescope where it was nighttime, and then they had to wait for another telescope further around the world as we turn, they found there was quite a significant difference in brightness on a cycle. And they figure that it must be tumbling. And if it's tumbling, it has to be 10 times longer than it is wide. Now, I don't know if that's the cause of the change in brightness. I mean, I honestly don't know, but that's a theory. I know one guy said, "Well, wait a minute, maybe it's a spacecraft from another solar system, and they want to check us out." Wouldn't it be neat if that happened? But I don't think there's conclusive evidence of that, and I'm a skeptic. So, but good question. Okay, have I answered your question, or do you want more?
Well, he's a major astronomer.
Yeah.
He's a major astronomer, and he claims that it's an artifact from somewhere.
Yeah.
And I just want to know if you know if you could tell us any more about the controversy.
Well, I mentioned the one astronomer that said that, comet Iceland is going to be as bright as the full moon, and he got lots of publicity because that's a sort of snazzy thing. And I'm very skeptical that it is an artifact from another civilization, in part because if I were from another civilization, I think I would monitor the Earth by radios, and you can set up great big disks further out in the solar system and maybe go into orbit in the solar system further out, and they could watch I Love Lucy or whatever TV show they want to watch. So I'm very skeptical, but I don't think an awful lot of professional astronomers put a lot of weight into it, but I can't be sure. Okay.
Thanks very much for this. It made me think. I can't recall if a comet has ever hit the Earth. Has that been some? There's enough of them that one. Not sure that was a comet, but have there been any documented cases of a comet?
Okay,
as opposed to
I
an
can
asteroid?
guarantee with certainty that a comet has hit the Earth sometime in the last 4 billion years. But I don't know of any specific cases. There are some cases. I saw a talk at Toronto Centre of somebody that there was a big explosion in Israel. I don't know, 1000 BC, something like that, near Jericho, right? And he talked about how it might have been something like a comet that exploded in midair. There's the thing that happened in Russia, I don't know, 1908, something like that. And it was an explosion, and you could see the trees were flattened out for a distance. But to my knowledge, there was no crater found. And it could be it was a comet that, when the heat of impact caused the whole thing to melt and just explode. So I think that probably was a comet. I'm not familiar with other cases, but I'm sure there have been lots of comets. Okay. Great questions, boy. Any? Okay. Oh, good.
Are all comets made of roughly the same thing?
I'm going to give you the answer that I love giving my students. I don't know. To me, they would have to be carbon dioxide and water and some mud-like material. But are other comets different? As they do more research in comets, it could be they're going to find one with a slightly different composition. Maybe if we can identify a comet and get its orbit and say, oh, that traveled at the speed that would take us from Vega to us in, I don't know, 5,000 years. And Vega was at the time that it came from, so it probably came from Vega. And it could be we're going to find that the composition of the dust around Vega is different. And it could be that will lead to the fact that the composition of Vega is different than us. And maybe the Vera Rubin telescope will uncover exo comet coming, and we might be able to do the detailed experiments, because again, when Oumuamua was leaving, they could just get pictures of the tail. Okay, I'm sorry I can't give more detail, but that's a really good question. Okay.
Any more from the audience?
Uh,
Oh, Betty.
I was wondering how large comets are, and if there's a size where a person might say, this is not a large, this is too big to be a comet or whatever. It's something else. Is there a size limit on comets, or how large are they on average?
Okay. By some criteria, comets are the biggest thing in the solar system because the tail can be over an astronomical unit long, but it's pretty thin. The nucleus itself is sort of the size of a small town or a city, and some are bigger than others. Okay. But they're not very big. And I should know the comet that Philae landed on. I used to know the size, but I think it's something like 6 kilometers long, but I'm not sure. Maybe someone knows. Okay, Betty? Okay. Yeah. Okay, good.
Can you just tell us a little bit about an anti-tail, and if you could see it in a small telescope?
Can I give you some advice? Look at the Astronomy Picture of the Day website. And about 2 weeks ago, and I almost poached the image and I decided I wouldn't, they had a picture taken by somebody, and you've got this glorious tail that's nice and wide and a very thin anti-tail. Now, there's something that the comet has an orbit and it's in a plane of the orbit. Remember, I mentioned that. And the dust ends up not just being pushed right behind it, but spreading over the plane. And when we're just in the right orientation, we can, if the plane is, if we're here and the plane is looking at us, we can see an anti-tail. But it's very rare. And I personally didn't see it on this comet because it was cloudy for, can I swear? No, I guess I shouldn't swear. But it was cloudy for a few days before it cleared, and by then the comet had mostly passed. Okay, have I answered your question? What's that? You can see it with your naked eye. Okay, and this was just a hand, well, not probably on a tripod, but it was a camera that took the picture, and it's just stunning. Okay, did one of you have a question? Because I wanted to show something else if I could. Oh.
Yeah, and we got some questions online.
Oh, great.
Yeah, we actually have a comment from Brenda Shaw who says, Avi Loeb is a name that comes with a big grain of salt. It's not a spacecraft or an artifact. It's a natural object. She follows that up with, oh, and this is another one. I will continue to remind people that the guy who thinks he found Sodom and it was destroyed by an airburst is the dean of an unaccredited evangelical Christian college.
Okay. 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 Can I just talk about a tiny more thing? Okay. After I had it all ready, I noticed something in the news. And there was talk that people had found evidence for a planet 9. And it kind of relates to all my stuff on orbits. And I decided I'll just put a tiny bit together. So I don't think I'll be 2 minutes with this. Michael Brown taught a course that I took on the solar system, online course, and just fascinating. Oh, just wonderful detail. And he gets a lot of telescope time, and he looks at very deep images of faint patches of sky. And he then takes another picture, I don't know, 1 day later or whatever, or, like I did with Pluto, and he finds moving objects, and then he finds the details, and he's quite skilled at this. This from Wikipedia shows the discoveries in the far solar system, and it shows the 3 outer planets that are 10, 20, and 30 astronomical units away. And the periods are given in red, but it's hard to read. Outside Neptune, you have the Kuiper Belt, and the diameter gives the idea of how big the dwarf planet is. All right. So these are the objects, and what he finds is when he, when they find the elements of the whatever the body's called, a planet or an asteroid. It's a planet if it's round, a dwarf planet if it's round. And from knowing the elements of it, you can work out that in this direction, say towards Antares, it's where the sun, if someone were on the sun, would see the thing at perihelion with Scorpio behind it. But then it takes its deep, deep trip into far, far away. It would be in Orion, which is the opposite end of the sky. So from these elements, you can work out where the comets, where these bodies go. And it turns out they're alleging for some of these, most of the objects are to one side. So it could be most of them are in the Orion direction and none in the Scorpio direction. Now, I don't know which direction it was, but I'm just saying. So what they're saying is maybe the reason there are no of these big objects in the Scorpio direction is that there's a planet 9 that is big enough to have disrupted their orbits and either shipped them into another place or whatever. And that news came out just yesterday. And this is their argument, but it's one of these things in science where it's not settled. And I love that, where they're still arguing back and forth, because some people think it's a new planet, some not. And they're trying to look where they think it might be, but it takes a lot of telescope time. Now, Eris is magnitude 18 and a bit. That's the biggest thing out there. So this might be magnitude 25, 26, and it's really stretching the ability to pick things up. So they might find the actual object, or it might be an argument in limbo. Anyway, I decided to add that in if there was time, and given that one speaker couldn't make it, I decided to add it. So anyway, if there are no questions about that, I'll let you get on with Frank's talk.
All right.
Okay. Thank you very much.